Assalamu alaikum and welcome to lecture number 9. In this lecture we are going to talk about quantization and encoding. So you know that we are studying in this course the one-dimensional signal, that is we have one independent variable and one dependent variable. So in case of time domain signal, we have two continuous variable which are time and the value of the signal. In the previous lecture we have talked about how we can continuous independent variable which is time into discrete variable which is represented as n by the process called the sampling. So that means now original signal, analog signal x of 80 now has the discrete version of this signal which is represented by xn, and n is basically an integer. So xn cannot be called a digital signal because although the independent variable has been discretized, but the value of the signal which is itself x of n, so x of n is not a discrete. The sample values of xn are still real and they have infinite resolution, therefore we cannot process them using a digital computer. So in this part we are going to convert this continuous value signal into a discrete or digital value signal. Hence, once we do the sampling and quantization, the resulting signal will have discrete values also. So the process of converting a continuous valued samples xn into a discrete or the quantized sample is called quantization. So shown in figure 1 is a device that is a quantizer and which does the quantization. That is, it quantizes the value of the signal. It is a non-linear and non-invertible system that transforms the input samples xn that has a continuous range of amplitudes into a sequence x tilde n that assumes one of the finite number of prescribed values. So at the end, at the output of the quantization, the quantizer, we have quantized values of the signal also. The process of the quantization is shown here. You can see that originally this is a continuous time signal or analog signal which has values between x maximum and minus x maximum. So the first step we did, you recall from the previous lecture that we have sampled it. So after sampling we have, instead of continuous variable, right, which is t, now t has the discrete value. So we get sample, for example, at here, at 0, at ts, at 2ts, 3ts, and so on. So I hope it is very clear to you. So after the sampling we have discrete values, right? At discrete instant of time we have values of the signal, but the values of the signal, as you can see, are still continuous, that it has value this one, here it has value this one, and so on. And you understand that the distance between the two successive values is basically the sampling time, and you understand what happens in frequency domain when we sample it. So the function of the quantizer is to assign these values to the set of values called quantization levels. number of the levels or quantization levels are generally in the power of 2. That is, we have either 2 level, or we have 4 level, 8 level, 16 level, and so on. So we can also say 2 power b. So if we have 2 levels, then we have 2 power 1. For 4 levels, we have 2 square, which is 4, and so on. So in this particular example, we have 8 levels. So that means we have to assign all the values present in this signal into these 8 levels. Okay, so for example, value at here, although the level is here, okay, so this is quite near to L7, so this is assigned to L7. Similarly, this value is assigned to L6, this is to L2, L0, and so on. So you understand, originally this signal has, for example, here a 2TS, it has value of this one, but now it is approximated or rounded to this one. So I hope this gives you idea that while we do the quantization, we are rounding it off. So that means there we are introducing some error into the signal. So we have two types of quantizer. That is, either the quantizer will have a uniform quantization, or it will have non-uniform quantization or spaced levels. For uniform, also called a linear quantizer, the spacing between the levels is constant. So this rounding off gives rise to an error called the quantization error, represented by En, and it is defined as the difference between the quantized sampled and the unquantized sample, right? So that is the quantized sample is represented by x tilde, so x tilde of n minus x of n. So this represents the error introduced by the quantizer. So I think you understand that this error can be positive or it can be a negative, and the range of this is limited to the step by 2, right? So minus step by 2 up to step by 2. So this is the range of this error. It is only valid when the signal falls in the range of quantizer, which is denoted by R. In other words, the range of quantizer should be adjusted from the maximum negative value, represented as minus x max, to the maximum positive value, represented by x max. The value of the input signal xn for a bipolar signal. You understand, bipolar means a signal that contains positive value as well as the negative value. For the signals that have only positive or negative values, we call them unipolar signal, and different distribution of the levels would be appropriate. For signals that have, if f max is not known, one can approximate it as x max to be equal to 4 times the standard deviation of the signal. Following this discussion, we can easily obtain the relationship as R, which is the range, right? So for a signal, so range can also be defined as the difference between the peak to peak length. Okay, so for example, we have a signal that has a positive peak amplitude of 10 and negative peak of amplitude as minus 10, then we can say its range is basically equal to positive maximum, right, minus the negative maxima, right? So this will be the range which comes to be 20, or in general we can say that this is equal to basically 2 times the x maxima, right? So this is the range of the signal. Now this range is divided into L levels, so we can say that maximum the range, which is equal to 2 times maximum, is equal to n into L into the delta, right, where delta is the uh, quantization step size, or it is also called the resolution of the quantizer. So that means we can write that resolution of quantizer, or the quantization step, basically equals to R over L. R, because R is 2 times the maximum, so we can say that this is basically equals to 2 times the maximum over L. An important point to mention here is that quantization error cannot be recovered, you understand, because we have rounded it off, so we cannot determine it. However, from equation 1 and 2, it is obvious that for a given quantizer's range, the error can be minimized by increasing the number of levels. Hence, for a sufficiently large number of levels, the amount of error is almost negligible. So we'll discuss about it, what happens when we increase the number of levels. So you understand that's the resolution, or the quantization step, is equal to R over L. So that means if we increase the number of quantization levels, then we can reduce the resolution step, which will result into lowering the quantization error. By the way, can you guess what will happen if we increase the number of levels? So definitely it will decrease the resolution, and it will result into smaller error. So what the cost we are going to pay for this one? We can study the characteristic of uniform linear quantizer, that is the using the characteristic curve. The characteristic curve is basically a graph showing the input signal values and the quantized signal values. Along the x-axis we have the input signal values, and along the y-axis we have the quantized signal values. Specifically, if you note that when the input sample is in the range, that is the value of the input signal in the range from 0 up to delta, the quantizer output is given by delta by 2. So for all these values we have delta by 2. So this basically compares what the input signal values versus the quantized signal values. So I hope this gives you some understanding. You read it, and if you have any question, we can discuss it in the live session. So the next topic we are going to discuss here is the encoding. The encoding is a process of assigning a unique binary code word to each quantized level. An encoder is a device that converts the sampled values into, sampled means quantized values, into a unique binary code word CN, as shown in the figure. So input is our quantized values, and the output is the B-bit binary code word. Generally speaking, an encoder is nothing but a lookup table that lists binary code words against each quantized level. The relationship between the number of levels and the number of bits required to uniquely represent each level is given by L equals to 2 power B. So for example, we have 3 levels, that is L equal to 3. So how many bits do we need? So the required bit is not 3 levels. In fact, if we let's take 8 levels, right? So if we have 8 levels, as we studied on the second, as we plotted on the in the second slide graph. So for example, there we had 8 levels. So how many bits are sufficient to represent these 8 levels? So number of bits required is basically 2 power, because 8 equals to 2 power 3. Okay, so basically to represent 8 quantized levels we need 3 bits. Or we can also take that because L equals to 2 power B, so if we take log of L to the base 2, okay, similarly on this side log of 2 to the base B, log of B to the base 2, we get this relationship, which is also represented here. Okay, so B will be equal to the number of bits required will be equal to log of number of levels to the base 2. So to represent it using binary code, we have different coding schemes, and each of them have some merits and demerits, or advantages and disadvantages, and depending upon our application we select the most desired one. Table 1 on the next slide depicts the coding of the 8 quantization levels using offset binary which is used in the pulse code modulation. So I hope by now you know about the pulse code modulation, because we have talked this one about so many times. Pulse code modulation is basically used in the standard digital telephony. So if we talk about this one, so basically the local loop, which is the connection between a telephone subscriber and the local exchange, is normally analog, but the inter-exchange communication, which is for example the communication between exchange in Ahmedabad to the Haripur or Islamabad or whatever, right? So the inter-exchange communication, that is digital, so they use the pulse code modulation scheme. In pulse code modulation scheme we use 8 quantization levels, 8 bit. They use 8-bit quantization. Okay, so that means if they use 8-bit quantization, then the number of levels can be found by using this equation, that in that case we have L equals to 2 power 8, right? So 2 power 8 basically equals to how many levels? So 2 power 8 means 2 multiplied by 2 multiplied by 8 times. If you multiply, so you get 256 levels. So that means in standard telephony we have 256 levels. In case of offset binary, the binary symbols are assigned in numeric order starting with the lowest level L0, whereas in 2's complement system, which is mostly used in computer and microprocessor for representing the sign numbers, they have the only difference between the two is the MSB. So in case of the 2's complement, if we simply invert the MSB means most significant bit, then we get the binary, the offset binary. So MSB is basically reserved for the sign, that is it represents a sign. So if MSB equals to 0, that means we have positive value of the sample. You know that we have in case of bipolar signal, that is a signal that have positive values and negative values. So for those signals the MSB is reserved, right? The most significant bit is reserved for the sign. So for the negative value of the sample, we use 1 for MSB, whereas for the positive value of the signal we have 0. So as we mentioned in the previous slide that we have a lookup table here. So this is for the 8 levels, right? So 8 levels can be represented by 3 bits, because L equals to 2 power B, where B is the total number of the bits, right? So you can see the offset binary or the PCM and 2's complement relationship. So you can see the only difference is the MSB. Okay. Otherwise, if you see the lower 2 digits, so they are same. That's 1 1. That's also 1 1. This is 0 1. This is 0 1, and so on. Okay. So if you interchange the MSB, you can go from binary to 2's complement, or if you are in 2's complement, you go to the binary or the PCM. So you just change the MSB. So just changing the MSB, you can go from one to the other. So an important parameter of the analog to digital converter is the bit rate. So you know that analog to digital converter basically consists of the sampler, which converts the continuous time variable into discrete one, that is x of t is converted to x of n, and because x of n still is continuous in values, x of n is discrete in its independent variable, that is it exists at distinct interval of times, but the values of this are still continuous. So to convert these continuous values into some discrete one, we use the quantizer. So we have analog to digital converter will consist of the sampler, you understand why, quantizer, and then it has an encoder, right? So that's all about the analog to digital converter that consists of 3 main parts. The data rate of analog to digital converter is usually expressed in terms of bit rate, and we represent the data rate by RB. So RB has units of number of bits per second, or in short we can say BPS. The bit rate is related to the sampling rate Fs by RB equals to B times RB equals to B times Fs, okay, where B is the number of bits per sample. So for example, we have a digital communication PCM system. So in PCM, you know that so for typical telephony channel, we can find the data rate, which we represent by RB equals to, you understand, that's number of bits multiplied by the Fs, or the sampling frequency. So for typical PCM, we have 8-bit. So we say that, okay, the data rate will be equal to 8-bit multiplied by 8 kilohertz. So 8 into 8, it results into 64, right? And K is kilo, and bit is, for example, represented by B, and hertz is basically 1 by second, right? So we can say, so for a typical telephone channel, we have data rate of 64 kilo bits per second, or we can also say 64 kbps. So you might have heard about the E1 carrier system, which is a digital telephony system that has data rate of 24.8, right, kilobits per second, right? So it has the capacity of 20.048 kilobits per second. So that means it can transmit how many telephone channels, because each channel is 64. So that means 64 into 32, right? So each E1 carrier can take 32 64 kilobit per kbps channels, okay? This is a digital telephony. As I told you that normally the communication between a subscriber, that is your house, and the exchange is analog, while the communication between exchange to exchange is digital. So that is their format. So that also means that the maximum frequency, what should be the maximum frequency of the voice that this telephony channel can carry, right? So you know that the sampling frequency is 8 kilohertz. So 8 kilohertz, right, is greater than or equal to 2 times the maximum frequency in hertz. So we just say Fn because we are talking about the linear frequency. So so the speech can have maximum frequency or whatever, whether it's speech or music data, whatever you are transmitting on the telephone line can have maximum frequency Fn, right? So Fn will be equal to how much? 8 kilohertz divided by 2. So that means Fn can be Fn, which is the maximum frequency, can be 4 kilohertz. Okay, so the maximum frequency is limited to 4 kilohertz. So that's why you can compare the quality of the speech you transmit or the music you transmit using the telephone system and those you hear on the FM system, right? So definitely FM system has much higher frequencies present in the speech or the music, so it has way better quality than the typical telephone system, right? So let's talk about two more things. What will happen if we increase the number of you understand sampling frequency is this one, but if we increase the sampling frequency, what happens? In the frequency domain, the replicas of the original signal are at distance that is equal to the sampling frequency. So if the more is the sampling frequency, higher will be the distance between the replicas and easier it is to reconstruct the signal, right? So even with non-ideal filter we can reconstruct if the replicas are far apart. Okay, so we double this frequency. What will happen if I double the frequency, sampling frequency? So instead of fs equals to 8 kilohertz, if I double it and make it 16 kilohertz, what will be the data rate now? So data rate will be doubled, you understand, because if I double it, the data rate will be doubled, right? So on E1 carrier we can has the data rate of how much? 2048 kilohertz. So that means it can transmit 32 voice channels, right? But if I double the sampling frequency, in that case the data rate produced by the each channel will be double. That is, now it's previously it's 64, but now it will become 128. So if I double it, that means the carrier can take half the channel. Instead of 32 channels, then we'll only be able to transmit 16 channels. So you understand, for the channels to maintain, I mean to transmit 32, we will need 2 E1 carriers. So you understand that in terms of hardware how much costly it will be, and also in terms of maintenance and so on, right? Again, if we increase the bits, for example, we represent something by 8-bit. If I represent something by 16-bit, what will happen? Because we know that the error is equal to how much? So the error signal is equal to, right, that's minus delta by 2, right? That's the error, quantization error, sorry, not error signal, quantization error. So quantization error is basically quantization step or quantization, right, by 2. So if I double the bits, then this will be half, right? The resolution or the quantization step size will be half. So when the quantization step is half, you know, if this is for example 1, so the error is 1 minus 1 by 2 up 1 by 2. If I half it, then it will be 1 by 1 1 by 4, So that means if I increase the number of bits, what will happen? The quantization error will be reduced. If I double it, the quantization error will be half. If I 4 times it, it will be decreased by the same factor. Okay, now so that means we want a system to have minimum quantization error. So to achieve minimum quantization error, we have to increase the number of bits. So for example, if it is represented by 8 bit, if I double it and represent it by 16 bit, it will have small quantization error, right? So if I double it, then the data rate will, you understand, again will be doubled. So I hope you understand the trade-off between the sampling frequency and the data rate and the quantization, number of quantization levels and the data rate. So I hope this gives you the idea why we would like to have sampling frequency as small as possible and why we would like to have the bits number of levels to be as small as possible, because number of levels, the relationship between the number of bits and number of level is, you understand that L equals to 2 power B. Okay, so if you increase the number of levels, definitely number of bits required to code to make a code word of this will be increased, and when we increase the number of bits, it will result in increasing the data rate, right? So we have to, then if we double it, then we have to use 2 E1 carriers to transmit the same 32 channels, because now we use one E1 carrier to transmit 32 64K bit channels. So if I double it, then it will carry 16. If I, for example, if I double the number of bits and if I also double the sampling frequency, that means the overall the data rate will be increased by a factor of 4. So that means now instead of carrying 32 channel, it will be divided by 4, which will result how much? 32 divided by 4, 8, right? So instead of carrying 32 channel, it will carry 8 channel, right? So you have to double, or I mean 4 times the number of lines already installed. So I hope this gives you a sense. Okay, so is it clear that number of bits doubling is basically the quantization error decreasing results into increasing number of levels, and increasing number of level will require increased number of bits, and increased number of bits will result into increased data rate. So to analyze the quantization error, we'll use a model of quantizer as shown here. So that's your this quantize, right? That's the input signal, which is x of n, discrete in time, but in value it is continuous. So at the output of this equal is the quantized level. So we can also say this quantizer we can equivalent it to something, because due to the quantization noise is introduced. So we can say that basically we can make equivalent circuit of this one as input and the noise, and that's the noisy output signal. So the model is exactly equivalent to the quantizer if we know the error signal, right? In most cases, En is not known precisely, so we describe it statistically. Specifically, we assume that En is a sequence of random variables where, right, where the statistics of En do not change with time, that is, it is stationary. The random variables of error signal are uncorrelated. That's we can say it's a white noise sequence, the error, right? The error sequence is uncorrelated with the quantizer input. So the probability distribution function of the error sequence is uniform over the range of the quantization error. You understand that it has range of equal to minus delta by 2 to plus delta by 2. These assumptions generally hold for the time varying signal with finite quantization interval, right? That means the interval or step size, which is represented by delta, if it's very, very small, then these assumptions hold. So let's do some more mathematics on the quantization error. So for example, here is the probability density function of the quantization error, and its range is from minus delta by 2 up to delta by 2. So if xn falls outside the range of quantizer, then the error could be much larger than plus minus delta by 2 due to clipping, because the peaks will be clipped. So we can write the first order PDF or probability density function of En. I hope you have done these things in the probability course. So we can write it like this. It has value of equal to 1 by delta for this range, and it is equal to 0 otherwise. So you know that useful measure of degradation of signal caused by additive noise due to quantization is signal to noise ratio, R, SQ, and R, and it is defined as the signal power or the variance of the signal to the quantization noise power, or the variance of the noise. So that's represented by this. So expressing it into dB, we can represent it like this. I hope you have understanding of the dB or the decibel. Now from the previous equation, from the slide of previous equation where we have shown the equation 5, the mean error is 0 and its variance can be calculated as sigma E square equals to integration from minus infinity up to this. But you can see from the previous figure that it is basically, it exists from minus delta by 2. Let me redraw here. So that exists from minus delta by 2 up to delta by 2, right? And it has value of amplitude equals to 1 by delta. So by putting these values, right, so integrating it from minus delta by 2 to delta by 2, right? Also the value of this is 1 by delta in this range, so we can take delta as common. So just let me write quickly. We can say that integration minus delta over 2 to delta over 2, and because this has value 1 over delta, so I can take this as common, 1 over delta, because it's independent of this. So we are left with E square and integration with respect to dE. So it will be, you understand, the integration of this will be with respect to E is E cube over 3, right? So we have something like 1 over delta, and the integration is E cube over 3, and the range is minus delta by 2 up to delta by 2. So by putting values, I hope it's quite straightforward that you'll get this thing. And because from the previous equations on the previous slide, you know that delta is basically equals to R over L. R is the range over number of levels, which are L. So by putting this, and again this is equal to basically 2 times or let me write, right? So you know that delta equals to R by L. R equals to 2 times max, right? So and L equals to 2 power B. So we can say that delta square equals to R over L square. R is 2 times max of this, and L is basically 2 power B. So on simplification you get this equation, right? So if we put these values in the equation, we get as the equation as on the previous slide, right? So we said that okay, so it will be 10 into log of this. Okay, putting all these values here in the equation you have seen in the previous slide. So on simplification you will get, right? So taking log of this one and again taking log of 3 to the base 10 will result into 4.77 this thing. So that's the final equation, right, that gives you the signal to noise ratio in dB. So what if a 3-bit quantizer has signal to noise ratio of 10 dB? Then what would be the signal to noise ratio if we have a 5-bit quantizer? So the final equation we got on the previous slide is basically based on assumption that stated earlier, which generally works well in practice for time varying signals having uniform distribution of amplitude over the entire range of the quantizer. However, in certain scenarios like the speech signal, the assumptions do not hold true perfectly. That's why for speech signal, a non-uniform quantizers are preferred as they give better signal to noise ratio for a given number of bits. The non-linear quantizer that are usually implemented by quantizer are usually implemented by non-linear transformation, and they are called the companding, right? And then after companding, then we use the uniform quantizer. A-log companding is one of the standard algorithm used in 8-bit digital communication. So in case for the speech communication, in case for speech communication in digital telephony, we use a non-linear transformation that is called companding. So A-log companding, there are different logarithmic scales for that, and A-log companding is used for the case of standard telephony. So I hope this gives you some ideas. See you in the live session for the question answer. Allah Hafiz.